Every single time you send a secure message, or hop on a Wi-Fi network, or even just visit a website with that little lock icon, there's this invisible shield protecting your data. But this shield, it isn't made of anything physical. It's made of math. Pure, beautiful, and unbelievably powerful math that's humming away silently on all of our devices. So let's dive in and take a look at this hidden world.
We throw the word encryption around all the time, right? But what does it really mean? How does your computer actually take a message and just scramble it so perfectly that only the intended person can ever unscramble it? It honestly feels like some kind of magic trick. But today, we're going to pull back that curtain and see the real engine that makes it all happen.
So the global gold standard for protecting digital information is something called AES. That's the Advanced Encryption Standard. It's what governments, banks, pretty much everyone relies on. And its incredible strength doesn't come from some complex lock and key, but from a really specific, really clever kind of arithmetic. And this is it. This is the hero of our story, the Galois field. Specifically, we're talking about a type called GF2 to the N. Now, the best way to think about this is like a custom-built mathematical universe. It only has a limited number of things in it, but inside this little universe, all the rules of math, adding, subtracting, multiplying, even dividing, they all work perfectly. No weird errors, no exceptions. And for cryptography, that perfection is absolutely critical.
Okay, so how do you build a perfect mathematical universe? Well, the answer actually involves something you probably remember from school, but with a really cool twist.
That's right, polynomials, expressions like x squared plus 1. But hold on, these are not the polynomials from your high school algebra class. We're going to give these a very specific, very strange set of rules to create a whole new system of arithmetic that's just perfectly tailor-made for computers.
And here's where it gets really elegant. The rules are so simple. First, the numbers in front of the x's, the coefficients, they can only be 0 or 1. That's it. A term is either there or it's not. And second, when we add things together, we do it modulo 2, which has this amazing side effect, 1 plus 1 equals 0. It sounds weird, but this one little rule is the key that lets us represent any string of computer bits as its own unique polynomial.
Okay, but without any boundaries, we can create an infinite number of these polynomials. To make our special finite universe, we need to set a boundary. We need a rule book. And in this world, that rule book is a special kind of polynomial called an irreducible polynomial. Just think of it like a prime number, but for polynomials. You can't break it down any further. This rulebook is what's going to keep all of our math contained and predictable.
So how does this rulebook actually work? Well, it's a lot like telling time. On a clock, when you go past 12, you just wrap right back around to 1. 10 o'clock plus 4 hours isn't 14 o'clock, it's 2 o'clock. We're doing the exact same thing with our polynomials. Anytime a calculation gives us a polynomial that's too big, we just divide it by our rulebook polynomial and take the remainder. It's a brilliant, simple way to make sure all the results stay inside our finite world. And there it is. That is the actual rulebook for AES. This specific polynomial is the unbreakable law of the land for every single calculation that happens inside AES encryption. Every transformation, every single byte has to play by the rules set by this one polynomial. It's like the secret constitution that gives AES its power. All right, so we've been talking about polynomials and rings and fields, and it might still feel a bit abstract. But this right here is the aha moment. This is where we build the bridge from all this abstract algebra to the physical ones and zeros inside your computer. Just look at this. We're using a simpler example here, but you can see that every possible polynomial in this little universe has a unique bit pattern that goes with it. And that's the whole key right there. The polynomial x squared plus 1 isn't like the bit pattern 101, it is the bit pattern 101. They're just two different languages for saying the exact same thing.
So the big takeaway is this entire complex mathematical world we just built, it's not abstract at all. Every single element in it, every number, is literally just a string of bits. For AES, every element is 1 byte, an 8-bit pattern. We've just created the perfect mathematical system for manipulating computer bytes. Okay, so now that we know our special numbers are really just patterns of bits, let's see how the math actually works. This is where the magic trick gets revealed, and you're going to see that it's surprisingly simple and, more importantly, incredibly fast. Remember that weird rule, 1 plus 1 equals 0? Well, guess what? Computers have an operation that does exactly that. It's called the bitwise XOR. So adding two of our special polynomials together is the exact same thing as just taking their bit patterns and XORing them. This is one of the absolute fastest things a computer can do. No carrying numbers, no complicated logic, just a single, lightning-fast XOR.
So addition is super easy. But what about multiplication? I mean, multiplying two big polynomials and then finding the remainder? That sounds messy and slow. But this is where the real genius of using this specific kind of Galois field really shines. It all boils down to another set of super simple bit tricks.
It turns out, to multiply any two numbers in our field, all you really need is a simple recipe for multiplying by x. And here it is. You just check the very first bit. If it's a 0, you just shift all the bits one position to the left. If it's a 1, you do the same shift, but then you XOR the result with a special constant. And that constant, that 0001111, it comes directly from our AES rulebook polynomial. So any multiplication, no matter how complex it seems, is just a series of these simple shifts and XORs.
So let's bring this all home. We've gone from abstract algebra to polynomials to simple bit operations. Why go through all this trouble? Why does this very specific kind of math matter so much?
Well, it really all comes down to three things. First, it's incredibly efficient. What looks like complicated math on paper just boils down to the simplest operations a computer can do. That leads to speed. XORs and bit shifts are ridiculously fast for a processor. And finally, and most importantly, security. This whole system is built on a rock-solid mathematical foundation. It's a closed loop. Every operation has a perfect inverse, which means everything that's scrambled can be perfectly unscrambled, and there are no weird mathematical holes or shortcuts for an attacker to exploit.
And that's really the ultimate takeaway here. The secret engine of modern cryptography is this beautiful, elegant bridge between abstract math and practical computer engineering. Galois fields let us create this perfect little mathematical world that can be built directly into a computer chip using the fastest, simplest logic possible. That right there is the secret to the power and speed of AES.
So the math of Galois fields is busy securing our private data every single day, working completely unseen. It really makes you wonder, doesn't it? What other elegant mathematical ideas are hiding just beneath the surface, quietly running this digital world that we all depend on?